So, welcome back once again, and we are going to talk about, we are going to extend the last lecture, wherein we obtained the lens maker's formula and we also obtained the lens formula. Okay, in by using the sign convention which we have discussed earlier. Okay, now to a double convex lens that we treated, the two foci, focus F and focus F dash of the double convex lens are equidistant from the optical center of the lens. So one focus is on one side and the other focus is on the other side. Notwithstanding what are the values of R1 and R2. Okay, the focus will be at the same distance, this way, this side and the other side. The focus on the side of the original source of light, for example in this case, this focus is called the first focal point and the other focus is called the second focal point. Okay. Now, for example, of the object, of the top of the object, there is a image which is over here. The image is the point where two rays from the object meet or appear to meet. Now there are a number of rays, in fact infinite number of rays that can start from a point and pass through the lens. All these rays coming from here, they will pass through the image point. Okay, or appear to be passing through the image point. Image is the point where two rays from the object meet or appear to meet in case of a divergent lens. Okay. In the case of convergent lens, I'm first time using convergent and divergent. Okay, they are right now the convex lens and the concave lens that you can. Okay. So of the many lines that can be there is convenient choice for the two rays. First, a ray which is starting parallel to the principal axis of the lens. Okay, after encountering the lens, it passes through the second focus F dash. Okay, F dash of the convex lens appears to diverge in the case of the concave lens from the first focus. Okay, first principal focus. Well, a ray passing through the optical center of the lens will proceed in the same direction without any deviation. After refraction, it will pass in the same direction. And the third is that a ray through F that will emerge parallel to the principal axis. Okay, so I have just drawn, I have tried to draw the convex lens and the concave lens. In this lens the image is inverted but it is real. In this case the image is erect and you can see that it's diminished in size, and we can say that this is a virtual image. Okay, so now what is desired of you is to make several drawings and obtain several image points. Look here, from this head to the tail of this object, for every point there is an image point, and that makes the image for the object. Okay, so ray through focus emerges parallel to, this has not been shown here, but here we have taken only two rays, one parallel which emerges and appears to be coming from the first focus, and then another ray which is passing directly to the center. Okay, now we take up the magnification of a lens, and it is defined as the height of the image divided by the height of the object, which is equal to V upon U. The object distance upon the, for erect and virtual image, M is positive. But for inverted real image, M is negative. So this is about the magnification. We'll use that later on also. Now next item for the lenses is the power of a lens, which is defined in diopters. This is a measure of the convergence or divergence which a lens introduces in the light falling on it. Of course, a lens of shorter focal length bends it more, and the longer one bends it less. I've just tried to draw a diagram, a ray diagram, where I have a ray which could have gone this way, okay, but instead it is going this way, and it diverges by an angle delta and passes through the focus. Of course, the image formation, etc., is also on the focus. This is the optical center of the lens. This is double convex lens that I've shown. The height of this is equal to h. So I can write for this angle tan delta will be equal to h upon f. Very simple. And if for the definition purpose we take the value of h as equal to 1, then this tan of delta turns out to be equal to 1 upon f. Or for a small delta, we can say that delta itself is equal to 1 upon f. Okay. And this is the definition of power. So this delta is equal to 1 upon f is equal to capital P the power. But the power is expressed, normally the F, V, U, etc. are taken in centimeters, but for the purpose of power, the focal length is measured in meters. So P becomes equal to 1 upon F, and the P is measured in diopters, which is 1 upon meter and represented by V. Let me tell you that the power is positive for converging lenses and it is negative for diverging lenses. Okay, and of course the zero crossing is there and the power is 0 for a plane slab. If it is, neither side is, or for it the either side is a plane surface. Next we take thin lenses in contact and the power etc. in that. So now we'll take up combination of thin lenses in contact. They could be convex, they could be concave, or there could be a combination thereof. And there we find that the focal length of the equivalent lens is related to the focal length of the individual lenses by a formula 1 upon f is equal to 1 upon f1 plus 1 upon f2 plus 1 upon f3 plus and so on. And the corresponding powers, they will be related as the total power is equal to P1 plus P2 plus P3 and the net magnification that we will obtain as M1 into M2 into M3 etc. Okay. Mind it that these values F1, F2, F3 could be all of them positive, all of them negative, some of them positive, some of them negative, and the power values also similarly can be positive, negative, etc. And the values of M1, M2, M3 can be positive, negative, and they multiply like that. In not such a properly drawn set of two lenses A and B, both of them are double convex lenses, and this is considered as the center, optical center, the contact point capital P. We see that there is an object over here on this side, and then there is a ray that falls onto prism A of focal length f1, and thereafter it proceeds and forms an image I1 on the principal axis here I1. There is something which you can check and draw your own this thing. This is this I1, the image produced by A. It serves as a virtual object for lens B, and the final image is formed at the point A. So we have U from here to here, and V1 from here to here, and finally V like this. Now let's see that we have the object over here, and for the combination the image is formed at the point I. Okay, so for lens A that we have here, I will get from the lens formula 1 upon V1 minus 1 upon U is equal to 1 upon F1. Let's call this equation 1. For the second lens, that is lens B, I'll write final image is V, so 1 upon V minus 1 upon U, that is 1 upon V1. Okay, this is equal to 1 upon F2. Call this equation number 2. Now add these equations together, then 1 upon V1 and 1 upon V1, that will cancel out, and we'll get 1 upon V minus 1 upon U is equal to 1 upon F1 plus 1 upon F2. Okay, and if the combination is regarded as a single lens F, single lens with focal length F, then I will get 1 upon V minus 1 upon U is equal to 1 upon F, that is the lens formula, okay, used along with the sign convention. So if we compare this with this, we find that 1 upon F is equal to 1 upon F1 plus 1 upon F2. Now, if there are many lenses in contact, close contact, and they have the focal lengths F1, F2, F3, etc., then we'll get this formula. Okay? Because first of all, I take this combination, then this combination with this, and this whole combination with the fourth one, like that, and so I obtain 1 upon F is equal to 1 upon F1 plus 1 upon F2 plus 1 upon F3 and so on. Just like the combinations of capacitors in series or the combination of resistances in parallel, so we have the combination of the focal lengths in close contact with each other, this kind of series. So if the values of F, F1, F2, F3, etc. are expressed in meters, then of course we'll obtain this as the power inductors. This also the power inductors, this also power inductors, and this also power inductors. So the total power system of the lenses that is there, they can be convex, they can be concave, they can be any possible combination thereof. So P will be equal to P1 plus P2 plus P3, etc. Like that. And the magnification from first lens, because the image from the first lens is taken as the object from the second one, and that for the third one, etc. So the total magnification also becomes equal to is given by m is equal to m1 into m2 into m3, etc., etc. So what I expressed here, okay, and this we have been able to argue and derive and you can attempt several questions which are described in your textbooks, okay, where the numerical values are given and you are supposed to obtain this thing. One thing that's an interesting feature is for the double convex lens, that sometimes the magicians, they have this double convex lens, okay, and they will show you that there is an image formation, etc., etc., and this is working, and then they put this lens in a liquid and the lens disappears. It's simply because the material in which we immerse it, that has got the same refractive index as the refractive index given by this lens, which serves as a kind of a microscope also. Okay, so we'll talk about those microscopes and telescopes, etc. later, but first of all, in the next lecture we'll talk about the what we call prisms and the dispersion of the prisms, how the prisms function, how they work, etc., etc. So long, see you soon.